Hey, okay, so I just had a quick hour to throw something together. So I just put together a review for exams 1 and 2. It's just basically me speeding through the first 2 exams, just to give you an idea of how to do solutions. You can always go back and play bits and pieces that you felt went too fast over and over again. Yeah, I hope this is going to help you. Now my babies are awake and they're going to start making a lot of noises, so I'll jump into it.
Okay, everybody. So this is going to be something like a speed run through exam 1 and 2. Just give you a quick review and talk about how to do all these problems. So let's go ahead and get started. So this is question 1 from exam 1. It says label each equation as an ordinary differential equation, partial differential equation, linear, nonlinear, and indicate dependent and independent variables. Okay, so to start off with, if we have only one dependent variable, only one independent variable, and independent variables appear here, 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 and here. So the independent variable is what you take the derivative with respect to. Then that means that we have an ordinary differential equation. So A is an ordinary differential equation, B is an ordinary differential equation, and C has 2 independent variables, and so that is a partial differential equation. Okay? Alright, now they are linear if the dependent variable only appears sort of on its own. So this is the dependent variable squared, so this is nonlinear. This one, the dependent variable is y, and each time it appears on its own, so this is linear. And this one, we didn't actually say what we should call that, but I'll tell you right now, this is what we call linear, PDE. But you didn't have to put that on the exam. Indicate dependent and independent variables. So here we have a dependent variable of x, an independent variable of t. Here we have a dependent variable of y and an independent variable of x. And here we have a dependent variable of u and an independent variable of x and t. Alright, and I think that's everything. Yep. Okay, so question 1, not too bad. We're 15% of the way through the exam. Alright, so now dependent, so we want to determine if the following is an explicit solution to the differential equation. So they give us this guy and they give us this differential equation. So what we can do is, well, we need to find y prime and see if it matches up with this. So let's go ahead and find y prime. So y prime is going to be 2e to the 2x plus 3e to the minus x. And now we're going to plug it into the differential equation. So in for y prime, we have 2e to the 2x plus 3e to the minus x is equal to, remember, it's coming from here. We have 9e to the minus x plus 2 times y. That is 2e to the, sorry, not 2e to 2x, but e to the 2x minus 3e to the minus x. All right, now we just want to see if the left-hand side and right-hand side agrees. So, so just looking at this piece right now. So this is going to be equal to, we have 9e to the minus x plus 2e to the 2x minus 3e, makes that 2 times 3 makes that 6. So minus 6e to the minus x. And that gives me 2e to the 2x plus 3e to the minus x. So right-hand side is equal to left-hand side. And so yes, it's an explicit solution. Alright, cool, done. Alright, next one. Determine whether the given relation is an implicit solution to the differential equation. Alright, so that means we need to use implicit differentiation. So they gave us this relation, and we need to see if it matches into this. Well, what we can do is we can take an implicit derivative. So y becomes dy dx. Ln of y becomes 1 over y times dy dx. And on the right-hand side, we get 2x plus 0. Alright, left-hand side, I can factor out dy dx. And this gives me 1 minus 1 over y is equal to 2x. dy dx now is, we have y minus 1 over y. It's equal to 2x. And that tells me that dy dx is equal to 2xy divided by y minus 1. All right, done. Yes, it is an implicit solution. All right, good. All right, let's go to the next one. Number 4. Draw isoclines corresponding to slopes 1, 4, and 9 with their direction markers for the differential equation y prime is equal to 2x squared plus y squared, and sketch the solution of the initial value problem where y of 0 is equal to 1. Okay, so remember, isoclines are all the points that match a particular slope. So for here, the slopes that we care about is y prime is equal to 1, and say that's going to give us 2x squared plus y squared. Also, we want 4, which would be equals 2x squared plus y squared. And we want 9, which would be equal to 2x squared plus y squared. Now, each one of these is going to give us a curve, and they all fall in the same family. So this is going to give me y squared. Well, actually, it's probably best to leave it there. So if you look at it this way, instead of 4, I put 2 squared, and 9, I have 3 squared. These are all going to give me ellipses. And so now we can go ahead and sort of figure out how to draw an ellipse again, if you don't remember. I like to figure out what the points on the axes are, and then after that I just sort of connect them. So for instance, if I just look at what falls on the y-axis, then I would, for the first one, I have 2 times 0 plus y squared, and that's going to give me y is equal to plus or minus 1. So let's call this 1. So plus 1 minus 1. This might not really be a very good scale. And then if I want to see what happens on the x-axis, then I just plug in y equals 0. So I have 2x squared plus 0. And that tells me that I have, let's see, 1 over square root of 2 plus or minus is equal to x. And so 1 over square root of 2, square root of 2 is about 1.414. And so that's going to be less than 1. So it's going to be tall and not squat. Right, so there we go. Oop, there we go. And direction markers. Let's put some direction markers in. So these are all guys with slope 1. So it's going to be, just like a 45-degree angle. And that's those guys. All right, now let's take a look at the next one. It is going to be, let's see, so we're going to have 2, if I just want the y-axis points, again, this is an ellipse. So I'm going to have 2 squared is equal to, say, y squared, and that's going to give me y is equal to plus or minus 2. And so it's going to put 2 here and 2 here. And then if I want the x value, then I'm going to have 2 squared is equal to 2x squared. And that's going to give me square root of 2 is equal to plus or minus x. Or plus or minus square root of 2 is equal to x is a better way to say it. Scribble, let's just erase it. Oop, there we go. Okay, and so this 1.414, and so it's not quite up to 2, and that's what we got now. So this is the next isocline. Alright, so this is at, say, square root of 2, and this is at minus 2, and this is at plus 2, etc. Okay, now this is slightly steeper, so I'm going to make some slightly steeper lines. These are a slope of 2, so it should be bigger than a slope of 1. Doesn't have to be super precise. This is just sort of a qualitative examination. And you can go through to the same sort of thing for the last one. That's going to be a 3, and something a little squat over here. And it's going to look something like this. So we're getting the idea of the pattern by now. And this is going to have a slope of 3, and so it's going to be really, really, really steep. I'm not sure I can really be more refined than what I'm doing here. Okay, so now the final thing is to figure out the solution to the initial value problem where y of 0 is equal to 1. So y of 0, so x is 0, y is 1, it puts me right here. And so we follow the slope of 1, and we keep going up here, and then it looks like we're going to be a slope of 2 here, and then we're going to be a slope of 3 here. It's going to go really, really high, and that's the best I can do. Okay, so that's the idea. Right, now let's go on to the next one. Okay, so now we're using Euler's method to approximate solution to initial value problem dy dx is equal to xy plus y, with y of 0 is equal to 1, so this is going to be y naught, and by the way, this means x naught is equal to 0. And we want to figure out, we want to approximate solution at the points x equals 0.1 and 0.2 with step size of h of 0.1. Now remember, y sub n plus 1 is equal to y sub n plus h times f of xn yn. And so we're starting off with y of 0, so y of 1 is going to be equal to y of 0 plus h, which we know is 0.1, times f of x is 0, y is 0. Might as well write that. F of x 0, y of 0. Okay, so y of 0 is 1, so I'll put 1 here, plus 0.1 times x is 0 right now. X of 0 is 0. So that's going to kill that first term, and plus y. So we go 0 plus 1, right? And so that gives me 1.1 to start. Yep. All right, now this is the point 0.1, 1.1, right? So x and y. This is my first estimate. My second estimate is y sub 2, which is going to be y sub 1 plus 0.1 times f of x1, y1. And this is going to be 1.1 plus 0.1 times, now we have 0.1 for x, and y is now 1.1 plus 1.1. All right, so it's not too bad as far as arithmetic goes. So it's going 1.1 plus, say, 0.1 times 0.11 plus 1.1, right? And that is 1.1 plus 0.1 times, say, 1.21. And so that's 1.1 plus 0.121, which is ultimately going to be 1.221, right? And that's the answer. Piece of cake. Okay, now for number 6. Let's find the general solution for y prime plus 2y is equal to x squared e to the minus 2x. All right, this is a linear differential equation. So what I need to do is I need to multiply by the integrating factor. So I need to identify what is p of x. Well, p of x is just simply the constant function 2. It's whatever is attached to the y. It doesn't include the y. It's just whatever is attached to it. So this tells me that mu is equal to e to the integral of 2 dx, which is equal to e to the 2x. All right, now I'm going to multiply both sides by e to the 2x, and what does that give me? It gives me e to the 2x y prime plus 2 e to the 2x y is equal to x squared. Now, we can recognize that the derivative of e to the 2x is that. So basically we have a derivative here times y, and then we have the original function times y prime. That is the product rule going on there. So that means that this is d by dx times e to the 2x times y is equal to x squared. If I integrate both sides, I get e to the 2xy is equal to x cubed over 3 plus c. Y is equal to x cubed over 3 then times e to the minus 2x plus c e to the minus 2x. And that is the general solution. All right, there we go. All right, number 7, and we wrap up exam 1. Find the general solution of the following differential equation. So we have dy dx is equal to secant squared y times x. Now this is a separable differential equation. So this is dy over secant squared of y is equal to x dx. And this tells me then that we have cosine squared times y dy is equal to x dx. All right, now we want to integrate both sides. Remember, if we want to integrate cosine, it's easier if we just do it like this. So we have 1/2 plus 1 plus cosine of 2x times y, sorry, not dx, 2y, dy is equal to x dx. All right, now integrate both sides. That gives me 1/2 of x plus sine of 2y over 2 is equal to x squared plus c. And up, that should not have been x there. That should be a y. Okay, there we go. And there's really no doing any better than this. This is an implicit solution. And we're done. Just because we have a y inside of sine and I have a y on the outside, there's no inverting that. So we're good there. Okay, cool. So that's exam 1. Let's jump into exam 2. Exam 2. Determine the following differential equations. Determining if the following differential equations are exact. So it is a matter of finding and just matching, say, m with n and seeing if dm dy is equal to dn dx. If this is so, then we say exact, and otherwise not. All right. So for A, what do we have? We have 2xy plus 3 for m. That tells me that dm dy is equal to 2x. Now on the other side, I have n is equal to x squared minus 1, and well, that tells me that dn dx is equal to 2x. All right, and so done, check, check, is exact. Now take a look at B. We have m is equal to y e to the xy minus 1 over y. And if I take the derivative with respect to y, then that's going to give me, by the product rule, we have e to the xy plus xy e to the xy minus 1 over y squared times negative 1, so that gives me a plus. All right, now let's take a look at n. n is equal to x e to the xy plus x over y squared. All right, dn by dx is equal to, but again by product rule, we have e to the xy plus xy e to the xy, and then we have plus 1 over y squared. So check and check. So this is exact. All right, last one, C. C gives us m is equal to theta, and now we're going to take dm d theta here, and that gives me 1, because if it's attached here, that means that you take the derivative with respect to the other variable, right? So now n is equal to, say, 3r minus theta minus 1. Then we have dn by dr is equal to 3. And so this is not exact, because 3 isn't 1. Okay, cool. Number 2. Solve the exact equation. All right, so we're told this is exact, so we're going to need to sit here and figure it out. And so remember, we are given m, and that is equal to 1 plus ln of y. And m is also df. I should really put partials. Sorry about that. So partial derivative f, partial derivative of t, right? So I can figure out that f then of, say, ty is equal to t plus t ln of y plus some constant with respect to t, which we'll call g of y. It can still be a function of y. All right. Well, now I know if I take the derivative of f with respect to y, then that's actually going to give me n. And so this is going to give me t over y plus g of y prime. And this should be equal to n, and that itself is t over y. So that tells me that g prime of y is equal to 0. All right. So then that tells me that g prime, or that g of y, is equal to some constant. And so then the general solution is going to be f of ty is equal to Now we're going to be given t plus t ln of y plus c, and we need to set this equal to 0, so it gives us a concrete curve. All right, there we go. That is the solution. Next one. Find the solution to the initial value problem y double prime plus 2y prime plus y is equal to 0 when y is equal to y of 0 is 0 and y prime of 0 is 1. Okay, so now the characteristic equation here is going to be r squared plus 2r plus 1 is equal to 0. And that tells me that we have r plus 1 squared is equal to 0, which tells me I have a repeated root of r is equal to minus 1. That gives us two solutions. Y1 is equal to e to the t, and y2 is equal to t e to the t. So what we have repeated solutions. All right, so now let's go ahead and solve this initial value problem. So our solution now is y of t is equal to e to the t times c1 plus c2 t e to the t. We need to figure out what c1 and c2 are. Well, I know if I plug in y of 0 is equal to 0, this is going to give me c1 plus c2 times 0. So that goes away. That tells me then that c1 is equal to 0. All right, now I know that y of t is in fact c2 times t e to the t, because c1 was 0. Now let's take y prime. Y prime is equal to c2 times e to the t plus t e to the t. If I take a look at y prime of 0, which should be 1 by the way, then that's going to give me c1 times 1 plus 0, and so that tells me that c2, that tells me that c2 is equal to 1. So ultimately we have y of t is equal to t e to the t is the solution to our differential equation. All right, next one. Brian's solution of salt flows in at a constant rate of 6 liters into a large tank that initially held 50 liters of pure water. So 50 liters, and here we have an in rate of 6 liters per minute, and we have an out rate of same rate, 6 liters per minute, right? And our initial, this was pure water in the beginning. And what else do we have? So the solution in the tank is well stirred, blah, blah, blah. And the concentration of salt in the brine entering a tank is 0.05 kilograms per liter. All right, so I want to know what the mass of salt is in the tank after t minutes. Okay, so here we go. We have dx dt is equal to the in rate, which is going to be 6 liters per minute, times whatever the concentration is, so it's 0.05, minus the out rate, which is 6 liters per minute, times the amount of water, so x of t divided by 50. All right, so that's concentration inside. Okay, so this is going to give me, say, 0.30, and minus, say, 3 divided by 25 times x of t. All right, now we need to solve this differential equation. It's a linear differential equation. So we're going to rewrite it as dx dt is equal to, plus 3 over 25 x is equal to 0.3. All right, my integration factor then is mu of x, or mu of t, is equal to e to the 3 over 25 t, just because this is p and p is constant, so it just gives me that. Multiply both sides by this and integrate. So what we end up getting is on the left-hand side, we have the derivative with respect to t of e to the 3 over 25 times x is equal to 0.3 times e to the 3 over 25 times t. All right, integrate both sides. So we get e to the 3, t there, over 25t. X is equal to 0.3 divided by 3 over 25 e to the 3 over 25t plus c. Now solve for x, so we get x of t then is equal to, say, 0.1 I'll just try and do this calculation. So we have a 3 here and a 3 here. Those cancel. It makes a 0.1 up there. And then we have 0.1 times 25. And that's 2.5 times e to the 3 over 25 times t. Whoops. We are multiplying through by e to the minus. We're dividing by that on both sides. So that's going to be plus c times e to the minus 3 over 25 t. Okay. So what next? All right, well, we know that it's pure water in the very beginning, so that we know that x of 0 is equal to 0. And so that tells me then that we have 2.5 plus c is equal to 0. So then c is equal to minus 2.5. Okay. So what do we get? So the answer to part A is going to be 2.5 minus 2.5 e to the minus 3 over 25t. And they want to know when will the brine solution reach 10%. What is 10%? So we're looking for when x of t over 50 is equal to 0.1. And so then if we plug everything in, we're going to get let's see, 2.5 divided by 50 minus 2.5 divided by 50. Let's not do it that way. Multiply by 50 on both sides. So we get 2.5 minus 2.5 e to the minus 3 over 25t is equal to 5. Okay, this should be an immediate red flag. We start at an initial value of 0, and as t goes to infinity, this guy is going to 0. And so this is 2.5, this is 5, and this is where we start. And as this goes to 0, well, this is going to end up dominating, and so ultimately we just get an asymptote here. So it never reaches that. Okay, cool. All right, that is number 4. All right, let's see. Number 5. Find the general solution for this guy. So we have y double prime minus 6y prime plus 5y is equal to 0. And so we have the characteristic equation of r squared minus 6r plus 5 is equal to 0. And let's see if we can figure out, does this factor? We have minus 5 and minus 1, and that'll give us that. Yep, so r minus 5, r minus 1 is equal to 0. So that gives me then that y1 is equal to e to the 5t, y2 is equal to e to the t, and the general solution is y of t is equal to c1 e to the 5t plus c2 e to the t, and we're done. All right, that was an easy gimme. And last one, we have solve a differential equation that's given by this with these initial values. And so let's see, we're going to have r squared plus 2r plus 2 is equal to 0. That actually doesn't factor, so let's go ahead and take a look at it with the quadratic equation. So negative b, so that's 2, plus or minus the square root of 4 minus 4ac. And so that's going to be 8 all over 2a. And so that gives me negative 2 plus or minus the square root of minus 4 divided by 2. And so we can see that it's going to be minus 1 plus or minus I, because this gives me 2i. Okay, so that means my solutions are y of t is equal to e to the minus t times sine of t, and y sub 2 of t is equal to e to the minus t times cosine of t. And so my general solution is y of t is equal to c1 e to the minus t sine of t plus c2 e to the minus t cosine of t. All right, now we want to match up with this initial value problem. So we have y of 0 is equal to 2, and on the right hand side, if I put in 0, we end up just getting c2 times this is 1 and this is 1. All right, and this guy was 0, so I killed the first term. So 2 is equal to c2. All right, now let's see if we can figure out what, if I take y prime of t, it's going to give me, I don't like this, but let's do it anyway. So I get C1 times minus e to the minus t times sine of t, and then I get plus e to the minus t cosine of t, and I get plus C2 times minus e to the minus t times cosine of t, and I get minus e to the minus t sine of t. Okay, and we already know what C2 is, and that's fine. Let's see, what is y prime of 0? That is 1, and so now let's go ahead and see what happens. When I put 0 in, this term disappears, this term disappears, this term becomes 1, and this term becomes minus 1. And so we're going to get C1 times 1 plus C2, but secretly I know that's 2, times minus 1, and that is 1. And so then I get C1 is equal to 3. So that is my solution. I get, say, y sub t is equal to 3 e to the minus t sine of t, and then I get plus 2 e to the minus t cosine of t. All right, done. All right, last one. Find a particular solution to this guy. So we have y double prime minus y is equal to 2 e to the t. First thing to do is just guess. So a particular solution would be, say, a e to the t. If I go ahead and plug that in, well, we know y particular double prime is going to be a e to the t. And so let's see what happens. That's kind of a problem, right? So if I plug these guys in, I'm going to get a e to the t minus a e to the t is equal to 0. And that helps nobody. So let's try a different one. So we know if we have a homogeneous solution on the right-hand side, what we really need to do is we need to multiply it by t. So let's say y particular t then is going to be a times t e to the t. This should end up working. So I get y prime, in particular, is going to be a times e to the t plus t e to the t. And then I get y double prime of p of t is equal to a times e to the t plus e to the t plus t e to the t, or rather I get a times 2 e to the t plus t e to the t. All right, now let's plug that in. So on the left-hand side, I'm looking for y double prime minus y of p. And so I get a times 2 e to the t plus t e to the t. Then I get, on the other hand, I get minus just y sub p, and that's a t e to the t. Well, multiplying all these guys out, I see that this term ends up canceling this term, and I'm left with 2a e to the t. But on the other hand, this guy tells me that this should be equal to 2 e to the t. And so when I take a look at that, that tells me a is equal to 1, and y of t is equal to t e to the t. Just for fun, we now see that y sub t being t e to the t not only satisfies this differential equation, but it actually satisfies, where was it? This differential equation. So there you go, fun fact of the day. In any case, yeah, so that's the first 2 exams, and I'll try to find some time to do exam 3 later. All right, have a good day, and I hope this helps.
Okay, so I hope that helped. So that's the first 2/3 of the class, all into like an hour. And hopefully that clears up a bunch of confusion you might have had about those first 2 exams. The final, if you're taking it, is in 3 days. And then we're going to have, and so in between then, probably tomorrow, I'll release the review for exam 3. So, in any case, good luck. And yeah, see you later.